Okay, so welcome to the 27th video in the Discrete Structures series, and this video is going to be the start of a new chapter, proof methods. And as a matter of fact, most of our videos are going to refer to proof methods until we reach the chapter of graphs and trees. So this is what we're going to be doing for a good amount of time moving forward. And in this particular video, inside of proof methods, we'll be looking into the idea of proofs, and then we'll be looking into formal and informal proofs. Next, we'll look at the most common terms used in the process of proofs, and they are theorems, axioms, lemmas, corollaries, and conjectures. And then we'll look into the ways of proving an implication. And the proof methods that we're going to learn today are direct proof, proof by contrapositive, then we have vacuous and trivial proofs. So we say that these two proof methods are indirect proof methods, and there is one another important indirect proof method, and that is called proof by contradiction. So the proof by contradiction is also an indirect proof method like these two. However, the difference lies in the fact that it is not used to prove an implication, it is just used to prove any proposition P. So these three proof methods are used to prove the implication P implies Q in one way or another. But there are situations where we do not need to prove an implication but a single statement. So consider root 2 is irrational. If you look into this statement, there is no if then. Root 2 is irrational by itself, not because of something else. So it falls on a category of proofs slightly different than the proof for implications. We will then have two proof techniques left, proof by cases and exhaustive proofs. And that is the overview. We'll be looking at these two topics in the next video. So let's get started with the idea of proofs. A proof is any valid argument that establishes the truth of a mathematical statement. So we already know what an argument is. An argument is a set of premises followed by a conclusion. And a valid argument is the one where the conclusion can successfully be inferred from its premises. And therefore the method of proof is the process of providing that valid argument to establish the truth of a mathematical statement or a fact. And let us quickly look into this idea of formal and informal proofs. So the formal proof is the type of proof that we've been doing for the last couple of videos. In a formal proof, we are not allowed to skip any steps and we need to mention each rule of inference that we have used. But in an informal proof, we often skip steps, we apply more than one rule at a time, and some common axioms are not stated. So let us say that I want to establish a theorem about circles. And let's assume this complicated theorem requires me to calculate the area of the circle at some point. So I will make use of the fact that the area of the circle is pi r square, but nowhere in my theorem will I ever prove this fact. So the point here is oftentimes when we are dealing with real world proofs, it is almost impossible to be able to list all requisites and requirements. And some steps in our proofs are often very simple and we choose to skip those steps. So an informal proof is designed more for easy readability and human comprehension. Our formal proofs have their own applications in algorithms. When we need to automate the process of generating proofs using computers, we need to use the formal techniques. Because formal proofs are developed with precise unskipped steps that is easier to reproduce on a computer. Next, we'll look at four technical terms related to proofs: theorems, axioms, lemmas, and corollaries. So theorem is a mathematical statement or fact that has been proven true. And in order to call something a theorem, we want it to be at least somewhat important. Less important results are often just called results or facts, and this is just done to separate the less important facts from theorems. Next, axioms or postulates are the facts used by the theorem during proof. Sometimes other theorems are needed before a theorem can be proved, and the prerequisite theorems needed for the proof of a theorem are called lemma. The lemma are the less important theorems that are used in the proof of the current theorem. Then we have the idea of a corollary. A corollary is a direct result of a theorem, and we also have something called the conjecture. So a conjecture is a theorem that hasn't been proven yet. So it is just a fact that people have made based on observations, data, or heuristics, but there is no formal proof to that yet. Okay, so those things will be called conjectures. And if you are interested, there's a famous conjecture called Collat's conjecture. And this is also called the 3n+1 conjecture. This is an unsolved problem. And the rule is so simple that even a third grader will be able to understand. If you have an even number, you take the half. And if you reach an odd number, you multiply by 3 and add 1. And when you do that, the conjecture suggests that no matter what number you started with, you're always going to end up with a 1. And this question is a millennium question. If you are not aware, anybody that solves this question will get $1 million. But for our purposes, let's just ensure we understand the ideas of conjectures. Alright, so that was an overview on proofs and different terminologies used in proof. Next, we'll discuss a couple of proof methods and then look into a couple of problems. And we'll try to understand 4 different proof methods using a single chart. So we're going to look at direct proof, proof by contraposition or contrapositive, vacuous proofs, and trivial proof. And like I discussed earlier, all of these 4 proof methods are methods used to prove the implication P implies Q. Okay, so let us have a look at these proof methods quickly and then we'll go over 5 or 6 numerical problems that I have. So first we have direct proof, and by the name, a direct proof will prove an implication directly. So in this proof technique, we assume P and then we prove Q. So that means we take our premise and we see if there is a way to reason into the premise, if we can apply the rules of inferences to lead us from the premise to the conclusion. And if such a way is possible, we have achieved a direct proof. Next, the proof of contrapositive comes from the contrapositive of this implication, which you know is not Q implies not P. And proving not Q implies not P will be able to prove P implies Q at the same time. So the proof by contrapositive will start by assuming not Q, and then we will move on to prove not P. And if we are able to do this, we are able to prove not Q implies not P, and that is also the proof for the original implication by equivalence. So we have next two types of proofs. These are not really important. So if you look into this implication P implies Q, we have earlier talked about the situation where P is false. We know that in an implication, if the preconditions are false, then the proof is automatically valid. Therefore, for this implication P implies Q, if I can show that P is false, this completes my vacuous proof. Because you're asking me to prove that if P happens, then Q should happen. And therefore, the main challenge in my proof will be to prove that Q will happen given that P happens. But if I can find that the premise P is false in the first place, I do not even need to proceed with the proof, and the proof becomes vacuous. Similarly, in this implication P implies Q, if Q is automatically true, then my proof is complete also. So let me write that down. For a trivial proof, all I need to do is to prove that Q is true. And if I'm able to show that Q is always true, no matter the value of P, the proof is itself complete. So in that sense, direct proof and proof by contrapositive are far more important than these ones, because these techniques actually require me to reason. I have to start reasoning from P and reach Q in case of this, and I have to start reasoning from not Q and reach not P in this case. And you can see here no reasoning is required. I can simply prove the premise to be false and be done here, and I can simply prove the conclusion to be true and be done here. Okay, so next we'll dive into a couple of problems, and the reason I put all the problems together is that I don't want you to guess which method we are going to use, because when you're really facing these problems, let's say in an exam, you don't know which proof method to apply. Now in your textbook, a direct proof question is always associated with the topic of direct proof so that you know a direct proof should apply. But we definitely want to be able to recognize questions and which proof method will apply in that particular question. So we'll look at all of the questions at once. Okay, so the first question says if n is odd, prove that n square is odd. So this is an implication P implies Q. P suggests that n is odd and Q suggests that n square is odd, and I want to prove Q from P. And one thing about odd and even numbers, anytime you see an even number n, you can substitute that with 2 times k, where k is an integer, and the idea is 2 times some number is always even. And when you need to generalize an odd number, you can simply say n equals 2k plus 1. Because 2k being twice the product of an integer is even, and when you add 1, it becomes odd. You are also able to use 2k minus 1, but this is just common. Okay, what proof method do I apply for this one? So how would I approach a direct proof? A direct proof would be approached by assuming that n is odd, okay, and then proving that n square is odd. So that would be a direct way to do things. And if I want to prove this indirectly, you remember I need to prove not Q implies not P, okay. So if I can start with assuming that n square is not odd, which is not Q, and then go on to prove that n is not odd, that will also complete the proof. And therefore, which proof technique should you apply? Well, it depends on the question. A common rule of thumb is to try the direct proof first, and oftentimes you won't be able to find a solution, or you will reach a dead end, and then you know that you need to apply an indirect proof of some sort. So for this particular question, let's attempt a direct proof. Okay, so we know that a direct proof starts by assuming that n is odd, and we need to somehow prove that n square is also odd. So I won't write any language here, but you start by writing n is equals to 2k plus 1. Okay, that will make n odd. And can I use this fact to show that n square is odd? So let me evaluate n squared, which will be 2k plus 1 squared. So this will be 4k squared plus 4k plus 1. And do you see an obvious reason why this number is odd? I do, because I can take a 2 common here, and then I get a 2k squared plus 2k plus 1. And you can see this particular number being 2 times something is gonna be even. And when I add 1, it's gonna be odd. So you can argue that this is in the format of 2m plus 1, which makes it odd. Okay, so look at the proof here. We are able to start by assuming n is odd and then proving that n square is odd. So this is an example of direct proof. Let's look into our next question. Okay, so this question suggests that n and m are perfect squares, and we need to prove that their product n into m is also a perfect square. So what is a perfect square? Let's say a number like 9 and 16. These are perfect squares because 9 is 3 squared and 16 is 4 squared. And the claim is if I were to multiply these numbers together, I'm getting a 144, which is also a perfect square. So that is what the question is asking me to prove. Okay, and let's attempt a direct proof again. So for the direct proof, we start by assuming that n and m are perfect squares, and we somehow need to prove that their product is also a perfect square. And what can I do to represent n as a perfect square? Let me call n is equals to k1 squared and m is equals to k2 squared. So since n is a perfect square, it should be the square of some integer and so should be m. Now let me take the product n into m and see what I get. When I multiply n into m, I get k1 squared times k2 squared, which you can see is k1 k2 whole squared. And this is enough to prove that n into m is also a perfect square. And it tells us that it is the perfect square of the product of k1 and k2. So if I look at here, 9 is 3 square, 16 is 4 square, and 3 times 4 is 12. So 144 is 12 squared. So that's how we reached our proof here. Okay, so let's look into another problem. If n is an integer and 3n plus 2 is odd, then n is odd. Okay, now let us see what happens if we try a direct proof here. So for the direct proof, I have to start with 3n plus 2 is odd, and then I have to somehow be able to show that n is odd. So I can say that 3n plus 2 is odd by assuming 3n plus 2 is something like 2k plus 1. So all I'm doing is saying 3n plus 2 is odd. Now can I use this equation to show that n is odd? Because simplifying for n gives me n is equals to 2k minus 1 by 3. And this does not help us very much towards proving that n is odd. Therefore a direct proof didn't work and we'll therefore go for an indirect proof. And we know that in an indirect proof, from the given statement P implies Q, we want to prove not Q implies not P. So if I want to read the contrapositive of the statement, I get if n is not odd, then 3n plus 2 is not odd. And not odd means even. So I'll start my proof by assuming that n is even, and I'll use this to prove that 3n plus 2 is also even. And doing that essentially helps me to prove this contrapositive, which is also the proof of my original statement. So in this case, we start by assuming that n is even, and now we ask the same question. Can we use this fact to prove that 3n plus 2 is also even? So let us see if we can. So we get 3 into 2k plus 2, that is just 6k plus 2, and then I can see this is a multiple of 2. And I can see that this is an even number. And this completes the proof, but the biggest takeaway is that we used the contrapositive method. We started by assuming that n is not odd and ended up proving that 3n plus 2 is not odd. That is the proof by contrapositive, and the reason I know to apply that method is because the direct method didn't work. Let's dive into one another problem. Prove that if n is equals to a times b, a and b greater than 0, then a is less than or equal to n, or b is less than or equal to n. Okay, what do we actually need to prove here? It's saying that n is the product of a and b. It is just a fact that is given to us. But we need to prove that if a and b both are greater than 0, then this must be true. So given this relationship between n, a and b, if you are given that a and b are positive numbers, then we need to prove that at least one of a or b is less than or equal to n. And let's try to look at this problem in a direct method perspective. Can I use the fact that a and b are both greater than 0 to show that a is less than n or b is less than n? See, it is always difficult to deal with OR statements. I don't know if this is true or this is true. But if I were to take the contrapositive of this statement, then this part will become negated and become the left hand side of my implication. And let me show you what happens when we negate it so that you can see the advantage. So if I take the complement of a less than or equal to n or b less than or equal to n, I can apply the De Morgan's law. It is either going to be a greater than n, and the OR is going to change into and b is greater than n. Because you know that when you are taking the complement of an expression that involves OR, you need to apply the De Morgan's law. So each proposition will change its truth value, and then the OR will be changed into an AND. So since a is less than or equal to n, the opposite will be a is strictly greater than n. Same thing will be true for b, and the OR will change into an AND. And the advantage of having this is that I can separately say a greater than n, this is also true. I can separately say b greater than n, this is also true. So that is another advantage of having an AND operation. So these two tips help me decide that I'm going to use an indirect proof method for this one. So we'll assume that a is less than or n or b less than or n is false. Okay. Now if this is false, its complement must be true. Therefore a is greater than n and b is greater than n. We get this by De Morgan's laws, because you know that this OR is false means both of these must be false. Okay. So a less than or equal to n must also be false. That should give me a greater than n, and this should also be false. So that means b greater than n. Okay, so next I want to be able to use this fact and show that these must be wrong. So let me start with my given premise. Now given that n is equals to a times b, and my assumption here suggests that a and b are both individually bigger than n. So this will be greater than n squared. And it's important to understand this. I am replacing this a with an n and b with an n. Now a and b are not exactly n. A is greater than n, b is greater than n. So when I replace both of them with only n, the resulting product n square is going to be greater than this value. And this leads to me n is greater than n square, which is also false. Therefore, by assuming that this conclusion is false, we are able to prove that the premise is also false. And that completes our proof by contrapositive. Okay, we'll look at a couple of more questions, and this should be really simple ones. So we need to prove that the sum of two rational numbers is rational. So we can just attempt a direct proof. We know that a rational number is any number that can be expressed in the fraction a by b, where a and b are both integers and b is not equal to 0. So let's say n1 and n2 are my two rational numbers, and it is asking me to prove that their sum is also rational. I'll assume that my first rational number n1 can be represented by the fraction a1 by b1, and similarly I'll assume the second number n2 to be a2 by b2. And when I add these numbers, so I add and take the LCM, I get this expression, and we should be able to see that this also looks like a by b, because a linear combination of two integers is also an integer, and so is the product of two integers. So ultimately what I have for n1 and n2 is also a ratio of integers with the denominator not equal to 0. Therefore with this direct approach I'm able to prove that the sum of two rational numbers is always rational. Okay, I'll leave one question and a couple of hints before closing the video. So look at this question. If n is an integer and n square is odd, then n is also odd. So let us see if we can apply a direct or indirect proof here. Let us attempt a direct proof first. Direct proof would require me to assume that n square is odd. So I could say n square is equal to 2k plus 1. And using this fact, I need to somehow show that n is also odd. But all I get is n is equal to plus minus root under 2k plus 1. And this doesn't give me very many hints about whether n is even or odd. So direct proof doesn't work for this. So we'll attempt a proof by contraposition. And the statement that I want to prove. So let me write that down. N not odd should imply n square is not odd. In other words, if you can assume that n is even and use that to prove that n square is also even, your proof is also done. So whenever n is even, n is just 2k, and when you square this will be 4k square, it will still be 2 times something. And since this number is 2 times an integer, it is also an even number, and that completes your proof by contraposition. Okay, so these are the types of problems that are commonly asked for direct and indirect proofs. We'll be closing this video for today. In the next video, we'll continue with the other indirect techniques for proof, and that will include the proof by contradiction, proof by cases, and exhaustive proofs. So I'll see you guys in the next video with those topics. Until then, have a good day and bye.